of air. Right, Ms. Kutsia, can you please inform the rest of CS214 that I will today cover information that's not in the textbook and they better sort it out. I'll hope that Wi-Fi holds, but I'll draw a lot on the board, so I suggest you sell your notes or something. This is your opportunity. Imagine a vending machine. Yes, these stupid things where you put in your money and you punch in a code and it sometimes spits out very, very non-banting chips or chocolates or things. And sometimes it doesn't, you have to kick it, and sometimes even that doesn't help, and you say words that your grandmother doesn't want to hear. So, imagine a computer. You put in a program, you compile it, you run it, and at every point during the execution of that program, you have a certain state, let's call it a state, a certain condition that your program is in. What would that condition be? Well, mainly for a simple little Java program, it's the values of the variables plus where am I currently in my execution, right? So I am in a certain state in my program. Then something happens. And typically that thing that happens can either be the next command, like increase the value of the variables, yes? So then I am in a different state, yes? So any computer system at a given time is in a certain state. An event happens and the system changes state to another event. That event can be internal or external. For example, if you try to read input, yes, that would be an example of an external event. A local change inside the system is an example of an internal event. So any computer system is simply a combination of states and then events that join the states together. Yes? A vending machine is your classical example of what we call such a state machine. Yes. A vending machine is in a neutral state. Nothing happens. Power is on, but it's just sitting there. It's in a neutral state. Then you punch in a code. Now the vending machine is in the state where it should ask you to put in the right amount of money. Then you put in the money and you press the button, and now the vending machine is in the state where it's supposed to kick out the chocolate. So, okay, let's take another example. I'm playing World of Warcraft. I don't, but my son does. So I watch over his shoulders. You are in a certain state, yes, because all the other non-player characters are around you in a certain environment. In the environment where you are, things are there. There's something you can pick up. There's something that might want to kill you. That is a state, quite a complex one, much more complex than the vending machine, but it is a state. Then something happens. You pick up the axe. All these things are very violent. You pick up the axe, yes? Now the whole system is in a different state, yes? Okay? So anything you can think of. I'm playing World of Warcraft. I'm writing the Hello World Java program. I am on my banking app trying to get that money that my father has just transferred to my account, right? Because I want to go out tonight. Everything, every single computer program is simply a state machine. You are in a certain state, an event happens and the program goes to a different state. Okay, does that make sense? Yeah, okay, right. These things we can call state machines, or if you want to, a finite automaton. Theoretically, it has been proven by no less than Alan Turing himself that anything that is computable can be computed by a finite automaton. A special kind called a Turing machine, but so anything that can be computed can be, for anything that can be computed, we can draw a finite automaton. Yes, in this graph format, I have a state which I'm in, an event happened, and I go to a different state. Okay. Incidentally, you've all seen the movie Enigma. My heertjie, dis nou julle huiswerk vir die naweek. You have to either read the book or watch the movie. Just get to know what Turing did, right? It's absolutely stunning. And in short, what he did was he said things are computable. How many of you are math majors? Yeah. So you know that Hilbert made a list of, I can't remember, 10 or 100 or so, very famous unsolved problems in the 1800s. 1800s? When did Hilbert live? Right. Anyway, but famously, he did not realize, and none of the mathematicians at that stage realized, that some things cannot be computed. Until Gödel came along. You have to read up on this. Until Gödel came along with his incompleteness theorem, which says if you have a formal system, there is always something that is true within the system that cannot be proven to be true using only the information in the system. You have to go outside the system to be able to prove this. In other words, mathematics cannot define itself. Yeah? Bertrand Russell tried to do that. He tried to describe the whole of mathematics from basic axioms up and then prove the whole, which is lovely, yes? But with the incompleteness theorem by Gödel, there would always be something that you cannot prove within the system. Right. If you need some holiday reading, the book Gödel, Escher, Bach by David Hofstadter. It's a very, very nice one to read, both for maths and computer science. Right, so some things are not computable. Have I thrown you with that one before? They're all things that you cannot write a computer program for, yes? And that is simply anything that potentially requires an infinite amount of information, because at any stage, you don't know whether you have to compute more or whether there is no answer. So read up on the domino match problem. Yes? But in this course, we assume that we only work with things that are computable. Okay, so if you give me a computable problem, I can draw a finite automaton, a very special one though, a Turing machine. So for the most difficult ones, for the more difficult problems, I can draw a Turing machine. But there are some simple problems like programming the vending machine, which would be okay with the simplest form of a finite automaton called the DFA, which stands for deterministic finite automaton. Yes? And a DFA is simply a state, an event happens, I go to another state. Okay? And the important thing in such a finite automaton is I have to start somewhere. So I have to have a start state, and then somehow you have to indicate whether you get an error or whether you get an acceptable final state. So for the vending machine, the start state is the neutral state. And then a successful final state would be where it actually delivers my chocolate to me. An error would be where that claw buggers up and I kick the machine. Okay, that is not good. That is an error. So in any finite automaton, we are very worried when we draw the model, whether when we end up in a final state or also known as an accept state. Same thing. Accept or final state, and that indicates success. And along the way, there may be a sequence of events that lead me to an error state. Right. And this is what my research is all about. So if any of you wants to do a PhD, there we go. Yes.
I want to make sure that I understand this. This can say be said like our GUIs for our project. It has a start state, we choose the puzzle size and dictionary. There's calculates and the final state is the answer of the word.
Yes, lovely, thank you. Absolutely. Okay. Incidentally, for those of you who have dreams of writing your own game engine, the Ingenuity engine is beautiful, and that is simply a DFA. Yes? A compiler, if you say Java C, or you say whatever button you press in your Eclipse, I don't do Eclipse. That thing is also a DFA. To compile a program, the compiler that you use is also a DFA, which incidentally next semester you will be writing your own compiler. Okay, right? Yes.
So the main characteristic of a DFA just has the beginning state and then the final state, or can there be intermediate?
Oh no, there are lots. Sorry, thank you very much. There can be lots of intermediate states. So I have a start state, and then I write its name in there, say it's state number 0, and then event small a happens, and I go to state number 1, and event B happens. If event B happens when I'm in state 1, I stay in state 1. This looks much like a graph, yes? I can have self-loops. I can have more than one arrow doing that. Then I can go to state 2, and let's say state 2 is a final state. I draw it with a double circle. just convention. But I must say what event. So let's say again, it's an A that brings me here. And then if I'm in state 2, any event A or B, just let me stay there. Okay. But no, let's say B lets me stay there. But if I get an A, I go back to the start state. This is a finite automaton. It's got a start, it's got a set of states. It's got an alphabet. The name of these events forms the alphabet of the machine. I start somewhere, traditionally known as that, Q0. I have, in this case, one final state, but I can have many. One start state, but I can have many final states. Okay. For example, in the vending machine, I might have a final state which is a neutral state. Because it's there, it's successful. The fact that it's not yet done anything is still okay. It's acceptable. And then when the chocolate comes out, might be another final state. And then I have a mapping. I have a table which says, if I'm in state 0 and I get an A, what must I do? If I'm in state 0 and I get a B, what must I do? What is the resultant state? Yes?
Just the events B and 1 and 2 that might be seen as the refresh button on like a Google page.
Depending on your model, it might.
Because it returns to states there or yeah.
Imagine World of Warcraft. I'm in a state. What is the event that happens? I walk forward. Is the rest of my world still exactly sort of the same? Yeah. So I walked forward, but it didn't really change the state of the automaton. That would be such a self-loop. Yeah. Or refreshing, yeah. Yeah. More questions. I need you to understand this. Anything that's bothering you? No? Okay. The reason why this machine is called a DFA, where does the deterministic comes in? Deterministic says, well, if I'm in a state and an event occurs, it is deterministic. There's only one other state, a unique state that I can go to. So I never have a choice on the same event. So if I'm in 0 and an A occurs, it is deterministic. There's only one choice. I can only go to state A, to state 1 on an A. Yes, I may go to, if I'm here, if I'm in state 1, it's still deterministic because if B occurs, I stay in state 1. I don't do state 1 or state 2 or state 3. I stay in state 1. It's deterministic on the event. So if you give me a state and an event, there's a unique answer to what the other state is that I go to. That is deterministic. Next year, you're going to do concurrency, which is not exactly the same, but it's the nearest analogy, I guess. If you're non-deterministic, then you have a choice. So it's Friday morning. I have Thursday morning, 7:30. There are two states. I'm in my bed. The other state is the computer science lecture in A407. Yes. And the event is my alarm went off. But mostly, as you can see this morning, there's a non-deterministic choice on what happens after the alarm goes off, right? I can either stay in bed on the same event. The event was the same. The state is the same. The event is the same. I either stay there or I go to class. So I can go to 2 different states on the same event. Okay? Right. And then it's a non-deterministic machine. And incidentally, Mwawi, who showed you the video on Monday, is working exactly on this issue on how to transform non-deterministic machines into deterministic ones. Very interesting. Okay. And that is about what you need to know about finite automata for the moment. So, are you all happy? More questions? So, let's do substring search. Classic one. Very often, even when I assume when you write your reports, you sit with a file and actually what you want is you want to know whether you spelled necessary correctly, because you often spell that incorrectly. So now you simply search, you Control F. I know you all use words still, okay? So you Control F or whatever you're using. If you're in VI, you / and so on. So you search for every occurrence of a certain substring within that larger text. Yes, that is something you often do, and then you replace. Okay, so the scenario is well known, yes? But since we do it so often, what is the most effective way? What is the most efficient way to do it? Because clearly all these editors that we're using can do it very fast. Well, depending if it's a Windows machine or Word or whatever, but mostly it happens quite fast. So how do we get these algorithms to execute so fast? Because if you think about it, just think about it for a moment. You have your text file, lots and lots and lots of characters, yes? Many of them, because you've been working very hard and it's a very long report. And now you want to search for this is the text file. And now you want to search for a certain pattern. Say a string of nice. You want to search for a string of length 4, the word nice, within this text file. Because that's a non-scientific word and it should not appear in your computer science reports. Now, what you have is a very long string in effect, yes? A long, lots of characters and 4 characters. So where can this string occur? Well, it can start at character 1 and be at 1, 2, 3, 4. Yes? Or if it's not there, it might start at character 2. You cannot compare all the words because you might make a common mistake like write a lot when you actually mean a lot, which you may not use in computer science reports, but anyway. So you want to search for this and replace it with this. Yeah, okay. So the word that you're searching for, your pattern, can start here. Yes, the first 4 characters, or it can start at the next character and be that 4 characters. And now you can see it is many, 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 many compares. How many compares? Well, if my text has n characters and my pattern has m characters, surely it's in the order of m times n. Because for every string of length m, I have to compare it to every character here for the rest of the length. Yeah, so that's a brute force method. And surprisingly, does that make sense to you? Yes, initially.
Shouldn't it be n minus the length of the word?
Yeah, in the order of. Yeah. So in this approximation, m times n, it's not exactly mn. Because you will not compare it to the last 4 characters here when you run over. Okay. Depending on the kind of strings that you're looking for, surprisingly, this brute force method can be very efficient in general, randomly in text. The reason being that your characters are distributed randomly in your text, yes? So mostly I can make the first comparison and see, oh, well, my first character that I'm looking at is not an n. So I need not compare with the rest of the word. And I can immediately go to the next character in the text and try again. Okay? However, there are many situations where you don't have this luxury, where your average or best case is actually MN. For example, those of you who are interested in biology, in bioinformatics specifically, if you look at genome sequences, you have a very small alphabet. C, G. Yeah. You have only 4 characters in your alphabet, and genome sequences are long. Yes, extremely long. So to search for a certain pattern in your original genome sequence takes very long. It's a whole research field, how to efficiently search in genome sequences. Okay, so brute force clearly will not work in this situation. Also, if you're looking at binary and you're looking for certain strings. Now, why on earth would I search through binary? One example is viruses. If I'm looking for a certain pattern, and I only have the binary files, yes. So that's what most of your virus checkers do. They go down to the binary level because the code is not necessarily in its uncompiled form. It's an executable that gets downloaded on your machine. So only the binary is there. So for the virus checker to see that this file contains the horrible code, they have to look at the binary sequence. Yes? And then my alphabet is even smaller, it's 0 and 1. Okay? So brute force will not work there. Okay? So let's have a quick look. The history in the book is interesting, page 759, you can read that. But let's look at the brute force code then. So on average, in general, if you write a text editor, this might actually be good enough. Why might it be good enough? Because you have a fairly large alphabet of 26 characters. And because of the random distribution of character sequences, to search for a given pattern, you very often break off after comparison of the first character. Okay? So if you want a quick and dirty comparison, you simply use brute force. Right? So let's look at the brute force code. I have a pattern and I have text. Text is my large file. The pattern is the thing I'm looking for. Yes. So what I do is I simply walk through the whole text from 0 up to n minus m, yes, which is where m is the length of the pattern. And what I do is I go through my pattern, and check whether the character there is in the jth character in the pattern is equal to the character in the text at position I plus j. Where does the I plus j come from? A, B, C, D, E. This is my text. I'm looking for BC. So this is my pattern. This is my text. So I keep my index I over here for my text. I keep my index j over here for my pattern. I starts at 0 and j starts at 0. All right. So in the beginning, I compare 0 and 0. Yes. Let's make it equal. Suppose these two are equal. Then I want to check whether this, then I increase j and I check the second character. And that must be equal to not text of I, but text I of how far am I in my pattern. Yes, so it's the second one. So it's I plus j that I'm comparing. Right. If it's not equal, then you simply break and you go to the next character in the text. Okay. It works very well. Brute force. And the example in the textbook, there they've got it written out with a value of I, value of j, your inner loop, and then I plus j. So they've got the text abacadabra and they're looking for abra. Okay, so A matches, yes. B matches. Where am I now? Okay, now I'm confused. What am I missing? I've got a text and a pattern, those two match. Oh yes, and those two match, therefore I am at position 2 already. Yes, it's the next one that I'm going to look at. And then I get a mismatch between the A and the R. Okay, and therefore I have to break out. And now this is the important thing. The moment when I find that I have a mismatch, what do I do with I? I goes to the next character, yes, but J backtracks to the start of the pattern, yes. So if you think about this a little bit, I always goes to the next start comparing, but J jumps up and down. There it's a 2, now it resets to 0, then it goes to 1, it resets back to 0, and so on. So J keeps on going back to the beginning of the pattern. So this whole idea of backtracking implies, oh, now I see what happened there, okay. This whole idea of backtracking, if we can make that more efficient, we can write a more efficient piece of code. Okay, so the I and the J in the backtrack. There's the proof. Proposition M is Fuchsia. Brute force searching requires roughly n times m character compare. So our cost model over here is a character comparison. Okay. In the worst case. Oh, before we continue to a more efficient implementation, what would When is a best case? You see, we wrote our code quite cleverly. The moment we have a mismatch, we break. The moment we have a mismatch, we break. And the moment we break, we continue. Yes? But so in general, I said because of the random nature of text, it works fairly well. We break very quickly and go on. Break very quickly, go on. So we very seldom go through the whole length of the pattern. Yes. But what is the worst case? The worst case is if the pattern and the text are such that the prefix, what is the prefix of a string? Is the first characters of a string. Yes, we talked about that last week. So if I have long prefix matches between my text and my pattern, the algorithm reaches its worst case. For example, suppose my text is a lot of A's followed by a B, and then 4 A's followed by a B. That is my pattern. I have to compare the A and the A and the A and the A. So it's 5 comparisons before I find the mismatch on B. Yes, I had to go through the whole length of the pattern before I found the mismatch. And look at what happens now. Now I actually, if you think about it, I plus j is already at position 4 when I find the mismatch. So now I increase I plus 1, I with 1, but then I have to retest all of these things. Yeah, I know I have 4 A's and a B, but I sort of have to backtrack and retest because the pattern might have started there. And now you'll see that I keep on repeating through the whole length of the pattern. I keep on testing the whole length of the pattern until I get a mismatch right at the end. And then only here do I actually find the match on the B. Yes? Somehow, if you look at it with your eyes, you can see that, oh wow, this A, B fits right there because the B is the first thing that matches. The B will clash with all the preceding A's. Yeah? But if you do it programmatically with your 2 for loops, you compare here, you find a mismatch, you have to go back with J and start from letter number 2 and then get a mismatch and start from letter number 3 and get a mismatch and so on. So you literally do n by m comparisons minus the length. Yes? So this is your worst case scenario. It is in a text format, obviously quite esoteric. This would seldom occur, but in other situations like your genome matching or your binary matching, this will occur quite often. Okay, so we want, for the specialist applications, we want to get something better. And the only thing we can do to make this better is if we can remember what we've seen previously. So in this case, I know that I saw 4 A's. Can't I remember that I saw 4 A's? Instead of rechecking all the time? Yes, we can. And what we do is we can do the so-called Knuth-Morris-Pratt substring search. Knuth-Morris-Pratt is somewhat intricate code. And what they do is they try to remember in the pattern, what have I seen previously? Okay, and if I know that, look at this. You are comparing text and pattern, but blindly, character by character, without thinking, what have I seen before? If you can, and you know, if you get to a certain point where you have a mismatch, you know that the previous characters matched. Yes. If you get a mismatch, you know that the characters that I matched up to now were the same. Yes, otherwise I would have broken out of the loop, right? So you have information both about the text and about the pattern. So why are you going back to the beginning of the pattern? Isn't there a better way? You have information already about the characters in the text and in the pattern up to the point of the mismatch. And Knuth Morris Pratt tries to exploit exactly that. What do I know about the pattern up to now? And the idea is the following. How Knuth Morris Pratt will remember how the pattern and the text matched up to a certain point is that they take the pattern and they pre-process the pattern quite intensively. Remember, the text is the long one, the pattern is the shorter one, normally. So you have the shorter pattern, you pre-process the shorter pattern to remember this matching information, and then you let it loose again. Right. So how do we pre-process the pattern? What we do is we draw up a DFA. Yep. We draw up a DFA which tells us if I am at a certain state in the pattern and I see another character which is a mismatch, I need not go back to the beginning of the pattern. I may, for example, only backtrack one state. So the pattern is processed into a DFA. And that enables us to do shorter backtracking so that we don't need to go back to the beginning of the pattern all the time. Yes? For example, well, often we do when there's no other choice. But for example, in this DFA, remember the abracadabra example? My pattern over here is ABA, BAC. Yes? So I simply take this pattern and note the following. Look at the correspondences in the pattern. I have an AB followed by an AB. Yes? So there's repetition in the pattern itself. And that is exactly what you can exploit. Okay? Therefore, what we do, for example, suppose I've seen A, yes, and I get another A. That means I don't have to go to the beginning of the pattern because I can count this A as the first one I've seen. Yes? What I want to see is a pattern, AB, AB. Now I am here. And I get an A, and I'm very happy because it's the first character in my pattern. So I'm in the text, I read an A, I'm happy because it's the first character in my pattern. Yes. Then I'm in state 1. I went from state 0 to state 1 because I read the first character of the pattern. Yes. Then the next character in the pattern is a B, but what I read actually in the text was an A. But if I get a mismatch, I expected B, but I read an A, I can stay in state 1. I don't have to back up my J to state 0 again, yes, because I know that between state 0 and state 1, I need to get the pattern A, yes. So if I back up, I would have to read again to get to state 1, but I know I have already seen an A, so that is, if I'm in state 1 and I get the A, I can simply stay in state 1 as if I have just moved from state 0 to state 1. Let's try another example. If I am in state 0 in the beginning, what I expect is to see an A in my pattern. So this is your index J. The names of the states, 0, 1, 2, 3, 4, 5, is your index J in the text. If I'm in state 0, I would expect to see an A, but whoa, look at this. In the text, I see a B. Okay, so I have to stay exactly where I am because I know what I expect in the beginning. 0 represents the start of the pattern. So what I expect to see is an A. So if I see a B or a C in the text, I simply advance I by 1 because I have to start from the beginning of the pattern, which is with an A. All right. If I have just read in my pattern, there was a match with an A. So I moved from state 0 to state 1. But then the next thing that I would expect to see would be a B. But it's not a B, it's a C. This buggers up the whole thing, so I have to go back and say, well, what was in the text was AC, but what I expected was AB. So now I have to go start looking for an A again to start the pattern off. Okay. And so on and so forth. You'll see that this machine is very easy to draw if you have a match. What I expect to see in the text is AB, AB, AC. So if I'm in state 0 in my pattern, and I get an A, I go to 1, get a B, go to C, get an A, go to 3, get a B, go to 4, get an A, go to 5. And then I'm happy I've matched the pattern. So what these back arrows do is they ask themselves, what is the shortest distance that I have to backtrack to still recognize the pattern? So it manipulates the value of J. So we'll tackle this on Monday again. See if you can get your head around this. And please, for Monday, see whether you can figure out why this works. Draw a piece of text, a lot of letters, look at this pattern, and then try and match the pattern, the text and the pattern by hand. Okay, and you'll see that J does not need to backtrack that far. Okay, good.